Have you ever wondered how people predict election outcomes? Or how a company figures out the odds that a new product will actually be a hit? Well, a lot of the time, the secret sauce is a really powerful tool called the binomial distribution. It's all about calculating the chances of success when there are only two outcomes. And today, we're going to break down exactly how it all works.
To see this thing in action, let's hop in a time machine and go back to August 2001. The dot-com bubble is bursting, there's panic in the air, and this really grim prediction comes out. 30% of all internet companies are on the verge of running out of money. Talk about a high-stakes scenario, right?
So, this is our central mystery for today. If there's a 30% failure rate out there, what are the actual odds that you'd see exactly 4 companies go bust out of a random group of 10? It's definitely not as simple as it looks, but don't worry, we're going to solve it together, piece by piece.
Okay, so how do we even begin to tackle this? Well, the trick is to simplify the problem a lot. Instead of getting overwhelmed thinking about any 4 companies failing, what if we just focused on one specific outcome? Let's just say the first 4 companies we check fail, and the rest make it. That's our first clue.
A great way to think about this is to imagine each company's fate is just like a coin toss. It can either fail or it can succeed. That's it, just 2 outcomes. This simple analogy is basically the foundation for everything we're about to do. A company running out of cash? That's like getting heads. Staying in business? That's our tails.
So let's zero in on this one specific events order. The first 4 companies we pick fail, F, 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 and the next 6 succeed. What are the odds of this exact string of events playing out?
Now, here's a really important piece of the puzzle. We have to assume that these events are independent. All that means is that one company failing doesn't change another company's chances at all. It's just like flipping a coin, right? Getting heads on one toss doesn't make you any more or less likely to get heads on the next. And this idea of independence is crucial because it's what lets us just multiply the probabilities together. And because each company's fate is independent, the math is actually pretty straightforward. We just multiply the individual odds. We take that 30% chance of failure, that's 0.3 for the first company, times 0.3 for the second, and so on for all 4 failures. Then we do the exact same thing for the 6 successes, each one having a 70% chance of making it, so 0.7. And what's cool is we can turn this whole process into a neat little formula. To find the probability of any one specific sequence, you take the probability of success, let's call it P, and raise it to the power of how many successes you have, K. Then you multiply that by the probability of failure, which is just 1 minus P, raised to the power of the number of failures. Okay, so we figured out the odds of one specific sequence. But that's not our answer yet, is it? Because the 4 companies could fail in any order imaginable. And this brings us to the second, and just as important, clue in our investigation.
I mean, think about it. The 4 failures could all happen right at the beginning, or all at the end, or they could be scattered all over the place. And here's the kicker. Even though the orders are different, they all add up to the same outcome, 4 failures and 6 successes. And the probability for each and every one of these specific sequences is exactly the same.
So you see, this completely changes how we need to think about the problem. We're not looking at a sequence anymore. We're looking at a combination. The real question is this. Out of our 10 available slots, how many different ways can we pick the 4 that are going to be failures? And wouldn't you know it, mathematicians have the perfect tool for this exact job. It's called the binomial coefficient, or you'll often hear it called n choose k. It's designed for one thing, counting all the possible combinations when the order just doesn't matter. And here's the formula for it. Now, it might look a little intimidating with those exclamation points. That's a factorial, by the way, but it's really just a way of calculating combinations. N is our total number of items, so our 10 companies, and K is the number we want to choose, so our 4 failures. This little formula gives us the exact number of ways those 4 failures can be arranged. And that right there is the second piece of our puzzle. All right, this is it. We have the 2 parts we need. We know how to figure out the probability of any single sequence happening, and we know how to count how many of those different sequences are even possible. It's time to put it all together. You know, when you break it down, the logic is actually super elegant. The total probability is just the number of ways something can happen multiplied by the probability of each one of those ways happening. Simple as that. And drumroll, please. Here it is, the complete binomial probability formula. You can literally see the 2 parts we just found. That first bit, the binomial coefficient, counts up all the possible ways our 4 failures can happen.
And the second part calculates the tiny probability of any one of those specific ways. We just multiply them together, and that gives us the final answer.
Now, this formula is a beast, but you can't just use it for everything. There are 4 key rules to follow. First, you need a fixed number of trials, like our 10 companies. Second, each trial has to have only 2 outcomes, like fail or succeed. Third, and this is a big one, the trials have to be independent. And fourth, the probability of success needs to stay the same for every single trial. Our .com scenario? It checks all the boxes.
All right, it's time for the payoff. We have the formula, we have our numbers from the .com bubble, so let's plug everything in and finally solve the mystery we started with.
So, after we run the numbers, 10 trials, 4 failures, and that 30% probability of failure, we get our answer, 20%. Think about that. Back in 2001, there was a 1 in 5 chance that if you just picked 10 internet companies out of a hat, exactly 4 of them would be on the brink of collapse.
But here's where it gets even cooler. The binomial distribution is more than just a one-trick pony for solving single outcomes. It can actually paint a much bigger picture of what we should expect to happen on average, over the long run. And that brings us to the idea of expected value. It's basically the average outcome you'd predict if you could run this experiment over and over and over again. And get this, the formula for it couldn't be simpler. It's just the number of trials, n, times the probability of success, p. So for our .coms, you'd expect 3 out of 10 companies to fail, because 10 times 0.3 is 3.
And if you look at the whole distribution as a graph, you can see some really interesting patterns. Notice how the shape of the graph changes. If you have a 50-50 probability, it's perfectly symmetrical, a perfect bell curve. But if one outcome is more likely, like in our .com example where success had a 70% chance, the whole curve skews over to one side. It's a visual way of seeing that higher numbers of successes are just more likely.
So there you have it. We went from a simple yes or no situation to a powerful tool for making predictions. But this is really just scratching the surface. I mean, what happens when you're faced with a problem that has 3 or 4 or maybe even an infinite number of possibilities? Well, that question opens up a whole new, fascinating world of statistics.